atmospheric scientist and a Doppler on Wheels project scientist at the Center for Severe Weather Research since 2008. She is very well trained. She has a slew of degrees. She has a BS in physics from Loyola University and an MS in physics and an MAT in teacher education from Miami University and a PhD in atmospheric science from Purdue University. So Karen has always been fascinated by the world around her, and after considering some other careers in architecture, patent law, and veterinary medicine, she ultimately decided that the observational studies of severe weather was it, and it kind of basically combined a lot of her interests. So her research mainly focuses on the kinematics and dynamics of severe convective storms, characterizing the low-level wind structure in tornadoes, and understanding the boundary layer winds and small-scale structures in landfalling hurricanes. Additionally, she is passionate about science education and regularly participates in outreach activities in schools, museums, festivals, and online through media interviews and consultations. And of course, in her free time, she's an avid TV watcher, traveler, yogi, a reader, hiker, coffee drinker, which I think we all need this morning, a sleeper and obsessive researcher of random products that she never ends up buying. So Karen, we're so excited to have you today, and I'm going to turn it over to you, and we are excited to hear what you have for us today.
Great, thank you. I'm excited to be here virtually, so I get to stay in my pajamas and drink coffee while I give a presentation, which is kind of nice. So I'll switch over to screen sharing here for a second. As many times as you do these Zoom calls, I feel like I'm still, it's like, wait, what, where? All right. So hopefully you see my title slide. I'm just looking to the organizers. Yes, okay, good, done. That was the hardest part of the presentation. So I do have a new affiliation, but it's not to be announced yet. So sometime soon you'll hear, but that doesn't change my work with the Doppler on Wheels and doing that kind of stuff. That's all still going forward. So I'm going to talk today about tornadoes. I was told I can't talk about hurricanes or any of those other things that I like studying. So just tornadoes. So this joke probably does get old, but the real storm chasers, obviously at some point, Twister was a thing, Into the Storm, and of course, the Discovery Channel show Storm Chasers, which if you did watch eons ago, you may or may not have caught a glimpse of me sitting somewhere in a Dow. Of course, this is, for all you who storm chase, you know this is really what storm chasing looks like. I never struggle to find these pictures. These are actually from this year. So this is, the inside of the Dow during various missions or ferries or waiting for storms to form. So not quite as glamorous as, Twister or Into the Storm. But again, anybody who's been out in the field sort of knows that's the reality. So in tornado science, I like to break things down very basically. And there's a lot of big questions in tornado science, but I'm kind of just focusing on two of these. One of them being tornado prediction. How do tornadoes form? And when tornadoes form, how strong will they be? And then when will a tornado dissipate? So really predicting what's going to go on with the tornado behavior. The other part of tornado research, which has been a lot of my focus for most of my time doing this, is the impact of tornadoes. So looking at how strong the winds are at the surface. And the winds at the surface, obviously, are the winds that impact where we live. There's been numerous field projects throughout the decades, both big and small. I tried to start when I was at least in high school naming these, but there certainly were people out doing research before this. Probably the project people start getting the most familiar with, and of course, the inspiration for Twister was the Vortex field project in 1994 and 1995. And then the next big field project looking at tornado research, these questions that I sort of outlined, was then the follow-up of Vortex 2 in 2009 and 2010. So almost a decade later, more than a decade later, another big field project went on. In the interim, there's been other projects, OU and NSSL, people down there have been very active in taking out their radars or their mesonettes, trying to study tornadoes. It's usually limited to, a handful of people going out to study this stuff. Where I'm at the Center for Severe Weather Research and then subsequent places, we've done projects called Rotate and then Twirl and Tiny Twirl and then Nano Twirl, depending on how many people were able to engage in these projects. Sometimes we have up to 30 people doing them and all of our instruments out, and sometimes we have 5 of us And we're basically doing a day chase in eastern Colorado. The rotate and twirl projects in particular have focused on the impact of tornadoes, so really trying to get these low-level wind studies. And that's different than focusing on the prediction part of tornadoes, because that requires different types of positioning of instruments and sometimes even different instruments out there. So I'm going to start with the fundamental question that, like I said, I've been personally researching since my dissertation, and then for the last, I don't know, 15 odd years. And I don't have good answers, so sorry, spoiler alert, but there are some answers. And this really translates, I'm looking at it from the science perspective. You could talk about different regions of the tornado, what's in contact with the surface and the tornado boundary layer. And I could go over all this and bore you. But what it really boils down to is, what are the winds like at the surface? What are the winds that are doing damage? And that's really important for engineers, people who are designing houses, people who are ranking wind speeds, people who are assigning wind probabilities in different locations and trying to decide what sort of design standards a particular area needs. They need accurate information about what's happening at the surface. As I'm sure most people know, the the best way, or the probably more common way that you see people talk about winds at the surface is the enhanced Fujita scale, which was derived, of course, from the Fujita scale, and then currently in the works is the enhanced Fujita scale, which is really putting in more damage indicators and more knowledge that we've been gaining from some of the stuff that I'm going to show you here. But it still boils down to wind speed is inferred from damage. So very rarely do you have actually wind speed measurements, whether it's from a radar or from an anemometer, at the location of these buildings. So basically, what engineers do, they have wind tunnel modeling, they have computer modeling, and they look at the damage, they look at the construction, and then they're able to infer a particular wind speed. So they're not inferring, 102.3 miles per hour did that. You're getting, 102 to 130 miles an hour could have caused that type of damage. So it's a very crude inference of what the winds are at the surface. Like I said, it also depends on construction, debris. So if you're downwind of debris, that impacts what's happening. And then in a lot of regions in the high plains, at least, most of tornadoes don't actually hit structures. And not only do they not hit structures, they also commonly don't hit trees or other sort of vegetation that you can get wind speed from. So punchline there is it's hard to actually get real wind measurements at the surface. Back in the day, and if you ever go down to Norman, I think this is in the Weather Center in their atrium, was trying to place instruments in the path of the tornado. And there are very good ideas and very good reasons with this, and they're the first ones to do it, but obviously there's been subsequent people, including the group I'm with, and looking at this, I don't know, they look way too happy to be deploying this in front of a tornado. But obviously it's very cumbersome. It's taking 4 people in that picture to lift it up. There's 4 people then that have to get out of the way of the tornado. So it's a very time-consuming process. And again, they only have one of them at the time that they were deploying. So putting something in the path of the tornado, I always feel like if you really want to get hit by a tornado, it's actually very hard. And it's true with putting instruments in the path of the tornado. Almost inevitably, they miss. For the reasons, like I said, you only have one of them, or people are just trying to get out of the way. So by the time you make the decision, the tornado sometimes is dissipated or changed direction. So another way of getting measurements inside a tornado, which a lot of people have turned to, is radar observations. And I know most people probably know how radar works, but very basically, it hits a bunch of stuff. You get a bunch of information back from that stuff, and you could tell how much stuff is there. So, oops, wrong screen. So rain, debris, cows, whatever that is, making this high radar reflectivity. Then the other thing you get there is something called Doppler velocity. And Doppler velocity is not actually the true wind speed. It is a very good estimate of the wind speed, but really it's measuring the particles moving in the wind. So if you have a cow, this Doppler velocity is actually the speed of the cow, not the wind itself. And then because of geometry and the way radars sample, if you're measuring something parallel, so if you're measuring a wind component that's along your radar beam, you actually are getting 100% of that component of motion, whether it's the cow or the wind. But once you start getting perpendicular, the less and less parallel you get, you're actually measuring 0% of the wind. So that's why you see this couplet here. So these blues, that's the strong winds towards the radar. These reds are the strong winds away from the radar. These other things aren't cleaned up radar. But you see sort of these whites then on either end. And that's because, again, you're measuring predominantly the perpendicular component. But radars, just radars like your regular 88D or most any stationary radar, they're often quite far from tornadoes. And the farther you get away, the higher in the atmosphere you're scanning. So you're scanning well above ground level, 100 kilometers out. Also, your radar beam for typical radars, that's about 1 degree, is about 2 kilometers wide at that point. So your tornado is, just a small subsection of what you're measuring. And then in the best case, you get some sort of, not in the best case, but in a lot of cases, you get a hook echo that looks like this. So here's your hook right in there. Here's your Doppler velocity field. And really what you're looking at there is the mesocyclone, not actually the tornado. So in comes mobile radars. This is the 1995 Doppler on Wheels mobile radar. They were very proud of it, and as they should be. This was actually the first scanning mobile radar. Before that, there were mobile radars out there, but they weren't conventional in the sense that you think of a radar now, that it scans through the atmosphere like you think of your 88D. There was something called continuous wave, which is different. So this is the first, I'll say, normal radar that actually was put on a truck and went out to measure wind speeds in tornadoes. And certainly we've progressed since then. This is the 2010 version of our radar trucks. This is also the 2020 version. But even though they look the same on the outside, I promise you things on the inside have changed in terms of radar processing and signal processing. So the truck itself might look the same, but there's a lot of the guts of it that have changed. And certainly a lot of it's changed since 1995. So what that means, and this is always sort of obvious, but maybe not, is that basically there's nothing great here. You just drive up to really close to a tornado, and the closer you get to something, the more you can see. So the closer, you put your face close to somebody else's face, the more detail you can see. And that's basically the same idea with a mobile radar, is that you're just getting very close to what you're looking at. So you're getting much more fine scale resolution. These radars obviously scan faster, and there's some other things too, but really the basic premise is you're getting close, and you're getting close to the surface. So again, what we're seeing, before I'm showing you, this is an 88D image. Again, here's your hook echo. But what you see with a mobile radar is you see a lot more detail. So in this case, this is the ball of the hook there. You can see that you get this clear reflectivity eye, and then Doppler velocity, again, same type of thing as I showed you before. In tornadoes, a lot of how we're scanning, since we're scanning horizontally, you could also scan vertically through them. Basically, it's scanning through an ice cream cone. So you're getting these horizontal cross sections that are sort of oval or circular shape that you're looking at. And here's an example of looking at a tornado back in 2012. This is just a cute tornado that have never done anything with, but I like showing it. It was actually a pretty stationary tornado. This is what we're seeing. So we're about 4 kilometers away from this tornado, less than 2 miles, and we're watching this tornado form. Tornado, actually, it's already formed. But some of the things you can see, if you're sort of used to looking at messy radar data, is that besides the tornado here, there's also this horizontal vortex that forms out here. So you see the horizontal vortex that forms, and then you certainly see this clear eye again that I was talking about, which you pretty much could not see with a stationary radar far away. So in addition to our 3 X-band radars, we went back to the 1980s portable stations. But in this case, basically what we do is we just have 20 of them. So instead of just having one big cumbersome one, we have 20 very easy to carry ones. So you could fit 4 or 5 of these in the back of a pickup truck. They have a low center of mass. So the steel plate here is a pretty low center of mass. They're 1 meter high. You could also put them on stands and get them higher. So in general, they're not very susceptible to being tipped over. Also, while the instruments on there are always pricey, for the most part, we just treat them as dispensable. So if we happen to be lucky and this actually gets into a tornado, we get all the observations up until the point that the instruments break. And that's perfectly fine. It's perfectly fine if that happened. And then this is just a flashback to Vortex 2. So this is how people really look when they deploy stuff in front of a tornado. That's Tim Marshall there, for people who know Tim. and they had deployed one of these pods and were getting out of the way of the tornado at that point. So what we're hoping to do with these radar data and these 20 pods is radar data we're getting, say, 10, 15 meters above ground level, which for the most part is about above house level. The reason being that we're still a little bit above house level is because you have to get very close to the tornado. So within, 500 meters or a kilometer to actually get stuff very near the ground. So in general, most of your radar observations are sort of at roof height if you're doing a good job. So what you want to see is you have your radar observation here. What happens between here? And that's what we're trying to do with some of these instrumented pods, is try to fill in what we see at radar level to what we see at ground level, and then relate that to damage. So we have a very complicated deployment strategy. Basically, we put a bunch of stuff in front of a tornado and hope it gets hit. That pretty much sums it up. But ideally, we have a couple of radars out there. So we're looking at the tornado over a long period of time, very close to the ground with very high resolution. And not only are we putting one of our pieces of instrumentation in the path of the tornado, but somehow magically we're getting 4 or 5 of these in the path of the tornado. Which that does is that gives you ideas of the profile of the tornado wind. So instead of getting a point measurement along a line as the tornado goes through, what you get is that same point measurement, but you get it at different locations. So you really get an idea of what slices of the wind look like at different radii in the tornado. Ideally, also, we'd like to be scanning a little bit in height because that will help us get those Z profiles. So we have these array of pods getting, the radial profile, and then with the radars, we hope to be scanning, anywhere from 15 meters above ground level to 20, 30, 40 meters above ground level. So I never know which to show, and people always ask what's my favorite tornado. And my favorite tornado is probably never anybody else's favorite tornado because it's, what kind of scientific data can we get from this tornado? Basically, and the worst, I don't look out the window. I probably don't even know what any of these tornadoes look like in real life. I have no pictures, I have no video, I have no anything after a tornado. All I have is the data. So my favorite tornadoes get ranked by what I could do with the data. And while there's a bunch of these that I have in black here that we've done analyses on or that we're currently doing analyses on, I'm just gonna do my favorite tornadoes, which I know I've talked about before, but these are really the ones that either have been well analyzed and have given us really critical results moving tornado science forward, or are in the process of being analyzed, and we think there's going to be some pretty good stuff coming with these. So to start, I'm going to start with Russell, Kansas. And this one, as all good tornadoes, that you get this kind of data, have a good story that goes with it. For anybody who was out there in the 2012 season, it was, if I recall, pretty bleak. We were trying to get these pods in the path of the tornado, and we always hold on to them because we're nervous that we don't want to deploy all the pods and then the tornado gets better. So we always have this strategy where we're just sort of sitting. So myself and my colleague, Josh Werman, he's like, we're getting them in. We're doing it. I don't care. I'm getting out. I'm taking these pods myself and I'm just putting them in the tornado. I don't care. So basically we had, this is a big year for us. We had our 3 radars out. We had 3 different mesonet vehicles. We had these 20 pods. So both of us were sitting here in Dow 7. It was after dark because why not? Why not make the story a little bit more interesting? We had one of the radars deployed up to the north on the same road, and then we had another radar sort of farther out if the tornado is going to keep going. So we're sitting there, the tornado forms. It's a pretty weak tornado, but again, it's sort of, the season's been a little frustrating. The day's been a little frustrating. We're sort of like, let's just do it. So he jumps out of the radar and jumps into one of the pod vehicles. And actually his driver was one of the old TIV drivers, somebody who had driven the tornado intercept vehicle for Sean Casey and his friends, if you recall that. So he gets into this mesonet vehicle. I start giving him tornado locations because I have to tell him, where to put these pods, where the tornado is going to be. So he needs to get to these locations. And I'm just giving him these locations. Nobody has any visibility because it's night out. And I'm like, all right, it's here, it's here, it's here, 10 kilometers, 20 degrees, whatever, 5 kilometers, 10 degrees. And basically I just, no, you're wrong, you're wrong, you're wrong, you're wrong. I kept getting all these radio transmissions and I'm like, I'm right. I know I'm right. And suddenly it goes quiet. And then they come back on the radio and, and I don't know where they're at. And they, are like, okay, now where? And I start telling them locations again. And I still get the, you're wrong, you're wrong, you're wrong, you're wrong. And I'm like, I don't know how to help you. I'm like, this is where it's at. So basically what ended up happening, they went quiet again for a while. This was a weak tornado. I really need to say that this was a weak tornado and really had no hope of doing anything. You can almost see from that path that it was a weak tornado. It sort of started forming and then it's like zigzagging north. So probably wasn't gonna do anything great. What ended up happening is when he jumped into the mesonet vehicle, they had their units as miles. So we always work in kilometers, always. I promise you, it's like NASA, we always work in kilometers. So, everything I was giving him, he was looking at miles and feet. So yes, nothing was matching up. Basically what happened is it got really windy at their location because what happened was the tornado hit them. And then it got quiet at their location and they didn't realize that the tornado hit them and they were talking to me again and they decided to drive north. The tornado also at that point decided to go north. And then they got quiet again and they got hit a second time. So they got hit, got quiet, they drove north, they drove right back into the tornado, they got hit again. Our radar that was sitting up here too also got hit. I don't know what the radar operators were doing out at that point, but they also were hit with the tornado. And then shortly after that, the tornado dissipated. So for all that drama and all this very weak tornado, there's key things that happened here. So this radar that got hit was scanning very low to the ground. The mesonet that got hit twice got 2 in situ observations. And then very close to that, there was damage incurred. So it was sort of the trifecta of what we're looking for in these data sets. Oops. So just as an example, what ended up happening, we were able to get data at 3.5 meters above ground level, all the way up to 74 meters above ground level. And we were scanning very low to the ground with our fancy rapid scan radar. So I'm just playing this because if you're ever sitting in a radar truck, I just always want to remind people, when you see the tornado disappear, it's hit you. So that was what they were seeing, the other radar truck. Like I said, I'm not exactly sure what they were thinking at that point, but obviously not moving. So the punchline again of this data set was not for the good story, but that helps, was that with this wind profile, this was the first and so far the only wind profile that gave you vertical winds in a tornado. So this profile showed that the winds, and this is a little complicated to read, but basically this one here is normalized to 10 meters, and 10 meters is a standard observation height that engineers use. So everything that's to the right of that means that it's stronger than it was at 10 meters, means that the winds were stronger than what you observed at 10 meters. So what that's telling us is that it varies as a function of time, but there's a lot of times where the strongest winds we're seeing are 5 meters above ground level. So the strongest winds we're seeing are very near the surface. And this is the first time that this has ever been documented. And this profile then has gone on, and engineers are using that actually in their assessment of how they do design assessments. So this is actually making it into one of the engineering standards. So a weak tornado, obviously it's not, you don't know if it's applicable to every tornado, but it's the only piece of information we have at this moment. And this, I'll skip through it. I like the pretty colors, but this basically was just relating this to something not as engineering, looking at tornado structure. So we were able to look at what the tornado structure was like very near the surface. And the punchline here is that we were sampling the inflow, which again is in the first time that this has actually been sampled. And this tells us something about how these winds relate to tornado structure, which is important for people doing modeling, because when people are modeling tornadoes, one of the big questions in the modeling world is how deep that inflow layer is in the tornado. And that impacts what the structure is like and then the wind distribution. But that was a pretty simple tornado. Most tornadoes, or a lot of tornadoes, are complex. They don't have just a nice velocity couplet, a nice inbound and outbound. This is an example from, I think, Mohall. But the idea here is this is sort of the main circulation, but embedded in here are 4 or 5 multiple vortices. So it's not a nice, simple tornado. There's these little beads of vortices rotating about. Other examples, I mean, we have data in 200 plus tornadoes. This is an example where you have two concentric circulations. Which one is the tornado? You see there's a tight one here, this debris ring corresponding to velocities here. And then there's a bigger circulation out here, but also corresponding to very strong velocities. And then similarly, you could see multiple vortices that don't have to be around the ring. Sometimes they're in the center, sometimes they're all over the place. And we have a name for that. We call that the chocolate chip cookie tornado because it's sort of like chocolate chips sort of embedded in different points. So again, the idea is that even though I showed you this Russell tornado, that's just a very simple tornado. Not all of them are like that. So this is 2016, another frustrating year, I should say, for a couple of reasons. But this was Sulphur, Oklahoma, not somewhere that you'd normally chase, probably better than Virginia, but probably not by much. It's hilly, it's tree, it's gross. When you're doing these low-level wind missions, I mean, you can even see in this picture here with Tim and his team, you see all these hills and trees, and that's horrible for radars because you're not able to get very close to the surface, and you're also not able to see much of what's going on. But Sulphur was a very complex tornado. It had a lot of multiple vortices, and I'll show you some of these images in a second, caused damage, and we sort of got a piece of instrumentation hit. So it definitely got hit by very strong winds, but not the strongest winds in the tornado. Quick overview, and these gray pieces are beam blockage. Again, this is southeast Oklahoma. This is the tornado, strong winds here, winds of over 97 meters per second, over 200 miles per hour. It's a very big tornado, very wide, and it has these multiple vortices at different points. So again, our not very complicated deployment strategy is that we try to put a bunch of stuff in front of the tornado and get it hit. Tim, we gave him explicit instructions of just put stuff in front of the tornado. So Tim did, which was great. They deployed a pod right here, and then they bugged out pretty quickly. And fun fact, you could see them right here at that radar sweep moving to the south at that point. So that's actually them in the Doppler velocity, escaping the tornado, cutting it pretty close, I'll say. And I think Tim knew that as well. But as you can see, the tornado is down here. It has a big core, so certainly this pod did get hit by the core flow, but not necessarily the strongest winds in the tornado. So at 1 meter observation level, we got winds of about 40 meters per second. If you just look at the gust of 1 second, we got winds of about 50 meters per second. And then in the actual tornado around the same time, we were getting winds of about 97 meters per second with the radar. Again, just because I like dissecting exactly where things are and we're trying to get these measurements. This is the pod observation. This is the mesonet observation. This is the very big tornado with these multiple vortices. And if you move forward in time, you see the pod observation here. These are in meters per second, just to confuse you. And then you also see the mesonet at that exact time fleeing too. So even though the mesonet's moving, it's still getting wind observations at a particular location as well. So yeah, this is their flee point of, oh my gosh, keep going south. And actually, if you YouTube it, I think there's another chaser was filming their great escape coming out of this. But again, very complicated flow, damage occurred with it, and we were scanning basically every 7 seconds. So we did take these observations from our pod, basically these yellow ones here, as a function of time. And what we're trying to do then is relate what we're seeing with the radar at that same location above the pod and see how those match up. And what we're finding, and this is actually starting to become pretty consistent, is that what we're seeing at 1 meter and then what we're measuring typically with the Dow at 15 or 20 meters, is we're seeing about a 50% reduction in the wind. So like I said, we're sort of seeing winds of 100 meters per second, and the pod at 1 meter is seeing winds of about 50 meters per second. And again, this is also good to know because we're trying to, get these common observations where a lot of mobile radars are getting them and trying to relate them to what's happening at the surface. And just to illustrate how many multiple vortices were happening in this tornado, the poor person I had to do this, I'm like, draw every multiple vortex you see, because we did want to start linking this with the damage. And these are a lot of the multiple vortices that he saw. And the punchline besides this horrible exercise and torturing people, was that a lot of the damage that occurred occurred at locations that there was a multiple vortex. So even though you had the big tornado, there was a smaller tornado or a smaller vortex at that location, causing these regions of enhanced damage. So the other fun thing about this tornado, and I use fun loosely, is that I didn't tell you that 2 of our 3 radars weren't working. So we only had the 1 radar working. But luckily for us, OU was out there with their Raxpol radar. They also had their own set of problems, but between our incompetence and their incompetence, we both did our separate analyses, but what we could also do is combine the 2 radar data sets. So from our 1 working radar and from their radar, we're able to do something called dual Doppler analyses, which basically means that us up here, them down here, tornado over here, we're triangulating on the tornado flow. And when you triangulate on the tornado flow, when you're observing it from 2 different angles, you get something beyond the Doppler velocity. You can get the dual Doppler wind fields. So what that means is you actually look at a vector wind field. So instead of saying the Doppler velocity, you could actually say the X component or the Y component. And then from the X and Y, you could actually derive the W component. So the cool thing about this is this difference between the 2 radars, the distance between them, is actually one of the shortest baselines. It actually is the shortest baseline ever. And normally these baselines are very long. They're like 20 kilometers or something like that. This one was 3 kilometers. And what that does is it allows us to resolve the vortex flow with these 2 radars. Normally when they're 20 kilometers apart, you're looking at the tornado, but you're not really resolving the tornado flow and the 3D winds. When they're really close together, you're actually resolving the tornado flow. So this is still a work in progress. But also just to give you an idea really quick, showing you what 2 different perspectives look like. In this case, this is the Raxpol radar, the OU radar, and this is what the tornado looks like at their location. And then us up to the north at the exact same time, or pretty close to the same time, this is what the tornado looks like at our location. So you could tell geometry obviously makes a difference how you're sampling the tornado. And again, when you can combine these 2 geometries, you could start looking at the 3-dimensional winds. So you probably can't see this too well, but these are vector winds here. So you actually see vector winds overlaid there. And these black squiggles and these red and yellow squiggles are vorticity, so showing you the multiple vortices. And basically where you have these red squiggles, those are multiple vortices that we're seeing not only with the radars, but also in these 2- and 3-dimensional wind fields. So like I said, this is a work in progress. It's been a work in progress since 2016, but that's sort of how the game goes a little bit here. And then quickly, Dodge City, probably pretty underrated because I didn't realize that we had actually gotten some good data in here. The Dow 7 radar data, oh, I don't have the picture. The Dow 7 at some point was sitting in a ditch. So I was busy trying to figure out how to get it out of the ditch. But people did deploy pods, and we had one of the other radars out there. This is an example from the Dow 7 radar. So even though we were in a ditch, we were still scanning. But we need to correct the tilt on that. This is a cool one because here's the tornado. You'll see that it dissipates off here. You'll see that a new tornado is forming. So what's happening there is you're getting the cyclic tornadogenesis process. So even though we're not looking at it with 2 radars, we're sampling both of these tornadoes. We're sampling the dissipation of this one and the formation of this one. But we also have pods, which we're able to actually get in the core flow. So these are the pod observations, and this is the tornado moving through that array. So looking at that, eventually we're going to do the same exercise that we did for sulfur, where we look at the wind speeds in the pods and compare that to the radar gates that we're seeing above that. Again, this is still a work in progress, but this 50 to 70% reduction, again, is sort of what we're seeing. So then I feel like we didn't get any good data for a while. Then 2019, this was our second tiniest one yet. This was really us doing day chasing from Boulder, Colorado. And we went to McCook, and I know Magnum, Oklahoma isn't really day chasing, but we did it anyway. This is from McCook. McCook really was the winner from this year, and we were able to get what I think are really great data for different reasons. Right here, this is from the radar. The star here is our radar. The tornado forms, These dots here are all our different assets, our pods, and also one of our mesonets. Also to people, if we deploy a pod, you probably don't need to park a mesonet next to the pod because we think the pod will get hit. But we see that a lot where people deploy the pod and then they like drive the mesonet back and sit by the pod. I'm like, well, the idea for the pod is that it's going to get hit. So that's why we have two close observations at that point. But what happened here, pretty good. Tornadogenesis happened. As you could see in the wind field, you see that the tornado forms. It's sort of this unsteady formation, and then really gets going for a little bit off to the north there. This is actually pretty typical of the tornadogenesis process where things kind of try, don't try, try, don't try. It's this complicated structure, and then it kind of gets going. And in the predictability problem, how long then the tornado is going to last when it forms? Is it going to be one of these 5-minute tornadoes, or is it going to last for 30 minutes? So there's always the question of where should you put your radar? Should we be up here, waiting for it to be there? In this case, we decided to deploy where we thought it was going to make the tornado, which again I think worked out pretty well. So us here. Our pod and our mesonets actually were impacted by the core flow, but the core flow at the point where the tornado was still in its genesis phase. So it certainly had not reached peak intensity at all at that point. But I think we were still able to get some pretty good wind observations in that case. Again, just showing this complicated structure. Tornadoes, aren't these simple balls that you see. Still looking through this again. 27 or so meters per second were our peak winds with the pod. And at that time, the Dow peak winds were about 43 meters per second. So again, fitting sort of within that 50 to 70% range. But in this case, we were closer. So we're looking at winds, 20 meters or so above these pods. I'll talk a little bit more about this one in a second. So then 2020, this really was the tiniest twirl yet. I don't know if anybody went out chasing during the pandemic, but it was a no-go for most stuff. We actually did stuff sort of aggressively, even though we were day chasing and mapped up. We went into South Dakota, which, although I feel like this is starting to become par for the course. Wyoming, certainly in Colorado. We did some stuff in Kansas. We went down to Oklahoma, and we went all the way there, and then we turned around right before that tornado. So if anybody remembers, I can't remember the day. We thought it was going to be better the next day, and we were worried we weren't going to get to it. So we actually drove all the way down to the border and turned around. So that's kind of sad. But I'm not sure if it was good or bad. Otherwise, and I promise I'm not talking about them, I'm just mentioning, we actually deployed for 5 different wildfires here in Colorado in the fall. And then we went down for 3 of the hurricanes this year. So Zeta, Laura, and some other one. I know that sounds horrible. Sally. They just were all in the same spot, and they were wet, windy. Hurricanes kind of blend together. But we did get some great data, I think, in hurricanes and fires, but not much in tornadoes. The one thing we did do, I will say, this is our proud moment, is we got a new system. We basically got what are called drifter sounds. So instead of soundings, which basically go straight up, you sort of inflate them to rise at 4 meters per second. These drifter sounds are a bunch of basically styrofoam cups, and they're soundings, and they have balloons. And what you do is you inflate 16 of these to actually get to a level of neutral buoyancy and then get taken in the cloud. So you use these to map out the winds around tornadoes. Penn State has been doing this, and they've been mapping out winds sort of outside the mesocyclone and in the the forward flank region of storms. But what we want to do is basically, just like we're dropping pods very near the tornado, we want to release these a kilometer from the tornado. And there is a big learning curve for us to doing this. We're radar and instrument people. So this was during a gust front passage out in South Dakota. This isn't really that interesting. I won't show you our botched one. But the idea is, we're trying to get practice launching these things into wind. So you see those go off. And the scary thing is they go horizontal for quite a while, and then they finally get something and go up. And you can see it takes a while for them to rise. So unlike a sounding, which you do have a problem with soundings, is sometimes they get caught in wires and stuff when you launch them in the wind. These even more so, because they're not meant to go up like soundings are. So there was that. I was trying to think of something that exciting that happened this season. So that was probably it. So I'm looking at my time. Yes, I still have a little bit of time. And I'm going to skip through a couple of things here. I'm just going to first talk a little bit about tornadogenesis. This is Goshen, Wyoming. And if you could hear me over this horrible video sound, I'll let this play for a second. So the one thing I want you to note in that genesis thing, and I'm sure you guys have all seen tornadoes form, but that idea of that steady, unsteady formation, and you could really see this one in the funnel cloud this time, you know, and that really affects, I think, when people think a tornado is actually formed. In this case, Goshen, just for what it's worth, had tornadic winds well before you could actually see the funnel. But you do see that it does pulse and the winds do change in time. So just really quickly with the genesis problem, I mean, Goshen's so old, but the reason it does keep getting shown and the reason it's still my favorite tornado is because it's really getting at the how tornadoes form problem. The idea, of course, here is that, you know, on radar, they all make mesocyclones, all these hook echoes, you look at them, some of these look fantastic, some of these don't look fantastic, and which one makes a tornado and doesn't is really hard to tell. The big thing, and sorry, I'm kind of going through this fast, is the downdraft. So people talk about the rear flank downdraft, or really sort of the rear flank, forward flank downdraft. They kind of merge together. And the idea being this Goldilocks idea, is that, you know, is it too buoyant? Is it not buoyant enough? It sort of has to be just right. And for the most part, Paul Markowski proposed this kind of concept in 2002. I think there's still a lot of credence to that idea in various different ways, is that we're still trying to figure out how you get these Goldilocks downdrafts and how you can actually predict in a supercell how you'll get this type of downdraft. Again, Goshen County, I'm just going to skip through it really quick. I could talk more about it later. The idea with Goshen, though, is that really this is the best ever sampled tornado. There's never been a tornado since 2009 that's been sampled this well, with multiple radars, multiple instruments, multiple soundings. So from the genesis perspective, what we were looking at is we're looking at not only the temperature of this rear flank downdraft, but also how much momentum was with it. So how much sort of push and oomph it was giving. So this downdraft did have the Goldilocks flavor. But the other thing with that is that parcels didn't originate from very high up. They originated sort of from the forward flank within a few hundred kilometers of the surface. And then it pulsed. So basically there was stronger, weaker, stronger, weaker. And a lot of times when this downdraft was stronger, what would happen is that the tornado would strengthen. And then when it was weaker or you couldn't discern these pulses or that a pulse was occurring, the tornado was either weaker, or during the genesis phase, there's sometimes that it actually was not tornadic strength. So now what? I just wanted to get to my now what really quick. I just wanted to find the worst picture of me ever, whoever did that. That's mean. So what are we working on now? A couple of things I just want to talk about quickly. McCook, which I showed you just at the end there in 2019. I call that sort of a miss, but the one thing that McCook and other tornadoes can be used for is, first of all, these pod measurements actually have thermodynamic information, and I'm going to return to that in a second. But what we've been working on recently is not just looking at our favorite tornado anymore, but looking at all the tornadoes. So what we've been trying to do is compile statistics of what the winds are like, and these have specific meanings, and I know this is a lot and it's right at the end, but really what I'm trying to tell you here is that there's 100 tornadoes that are going into this, and we're looking at sort of the average wind speed that we see, and then the distribution of wind speeds. We're looking at the average size that we see, the distribution of size, and then how that relates to F scale or EF scale, depending on when. And then this is just a complicated way of looking at how winds increase or decrease with height. So everything that's in this region here are winds that are decreasing. So everything to the left here are winds decreasing with height. Everything to the right are winds increasing. And then this magic region here for tornado observations we have below 15 or so meters above ground level a lot of times that we see that those are the maximum wind speeds that we're seeing, are the ones that are very near ground level. Again, like I said, we also get thermodynamic information. This is a big thing that we're working on now, not only from this McCook case, but from a lot of other cases where we've been trying to get these low-level wind speeds, and basically we don't. We get, rear flank downdraft stuff. But again, we're getting thermodynamics, and to not get into too much detail, the idea with that is we could be looking at these temperatures of these downdrafts, how these downdrafts fluctuate both in space and in time. So lots of plots, which I just said. Also, dual Doppler analyses. We have 17 tornadoes that we've sampled with more than one radar. So we could not just look at Doppler velocity, we could derive these vector wind fields. And this is just to wow you with how many we have. But the idea here is that we're not just looking at my favorite tornado, this tornado did this. We're trying to look at how these tornadoes fit in the spectrum of tornadoes. And last but not least, what are we up to now? One thing I just want to tell people, we built a brand new Seaband radar. This is the only one in existence. It's deployable, it's a 1 degree. We deployed it down in Argentina a year ago. So it's unlike the Dows, you don't just drive up or drive and scan. Basically, it's assemblable. So we have a crane and we assemble it on site. It takes about 2 hours. And we do a lot more than tornadoes. So these are examples of different projects that we've done. And then last but not least, Perils, a project that was supposed to go forward this spring, but due to COVID, it won't. This is part of, if people have heard of the Vortex Southeast project, this is a bigger version of that. So looking at tornadoes that form in quasi-linear convective systems in the Southeast. And this is a partnership with the Vortex Southeast efforts of NOAA, NSF, and then hopefully DOE will be doing something down there as well. So it was supposed to be this spring and next spring, but we think it's going to be in 2022 and 2023. So with that, I will be done.
All right, that's a whole lot of information in a short period of time, but I tell you what, I was geeking out. I bet a lot of other people were too. For our folks that are monitoring social media and the YouTube chat, do we have any questions we want to bring up?
Bill, I think you're muted.
Can you hear me now?
Yep.
Yes, John Calvin asks, was wondering if it is easier to isolate rotational forces in very weak tornadoes.
Isolate rotational forces. I'm not 100% sure what he's asking.
He said, he just asked, was wondering if it is easier to isolate rotational forces in very weak tornadoes, and quoting his post on YouTube.
Yeah, I'm trying to think. I mean, so it's certainly easier to sample weak tornadoes because you can get closer to them than you can for strong tornadoes, or at least smaller weak tornadoes we tend to get closer to. So we have a bias, towards lower sampling in those. So in that sense, we probably get better low-level data than we would in stronger tornadoes. So we might get more information. Stronger tornadoes on the flip side are bigger. So it sort of depends, and it also depends on tornado structure. I mean, a lot of times, I guess in terms of isolating, sometimes it's hard to deconvolve what's tornado, what's RFD, what's this, what's that. So I'd say simpler tornadoes, whether or not they're weaker, it's debatable, but simpler tornadoes it's easier to deconvolve those from other storm processes, and in particular the winds.
Cool. Any other questions from social media? Because I have one.
Nothing from, I don't see anything on the Twitter feed.
Okay.
I was looking, but I didn't see anything.
Okay. Karen, the question I'm going to bring up, I know Brent is intimately familiar with, especially from this year, just chasing here in Virginia, in his market area. I came across at least 3 different storms with hook echoes on them. And my question, and none of them produce tornadoes as far as we know. My question is, is there some kind of formula, like what percentage of hook echoes create tornadoes, or is there a number that you can associate with that?
Yeah, I mean, the conventional number is that basically 75% of mesocyclones don't make tornadoes. And that's probably about right. But yeah, I mean, the majority of them don't. And again, 75% is the number people use, and I think that's still probably the right answer.
Anybody else with a question?
I have a question. How often do you guys get into the Southeast? Because we know a lot of the research is focused across the plains where things are more wide open, but we also know that we have so many more deadly tornadoes across the Southeast. Granted, it is a more difficult area to chase, and I'm excited for the Perils program because of the research with the QLCS tornadoes. But how often do you guys actually get into the Southeast?
Yeah, so we have not yet. So the Vortex Southeast project, which I think has been going since 2016, has been a NOAA-funded project. And part of it's been, and I don't mean this in a bad way, I mean this in a necessary way. I'm going to say a fishing expedition. And that sounds bad, but I don't actually mean it like that. Because it's trying to figure out how to sample in the Southeast for all the reasons that you said. That, you know, there's hills, there's trees, there's low visibility, there's high relative humidity. You get what's conventionally called the high cape or high shear, low cape events, where you have a lot of shear, but not as much cape as you conventionally get in the high plains. So this project Vortex Southeast has been going on and really trying to narrow down the problems in the Southeast and the problems that are tackleable by instruments and by mobile radars. Because looking at what I'm showing you, trying to get tornado wind speeds, 15 meters from the surface, that you can't do that in the Southeast. So what can you do and what are the problems? And quasi-linear convective systems, and also these sort of weird hybrid modes that seem to happen in the Southeast too, where you're kind of a supercell and it's kind of a QLCS type thing, really aren't as well understood. You don't have this mesocyclone. I mean, so supercells in the Southeast, I'll say, are the same problem as anywhere, right? I mean, you get a mesocyclone, you probably have 15 or so minutes warning. But these hybrid modes and these QLCSs, you have very little warning time and very little understanding actually of how they make tornadoes. So we're excited for this Perils project. Like I said, NOAA's been doing this, but now we're going to try to have this NSF component, and then also potentially DOE independently might be down there, and then collaborating with us. So look for 2022. There might be some little small thing this season, but really 2022, there should be an armada moving in there.
Dr. Kosiba, there was a question on YouTube from Peter Forrester. Do you anticipate using the Seaband radar for tornadoes? How will you catch a storm with that 2-hour setup time?
Right. So the Seaband radar isn't necessarily for tornadoes in the same way as the Dows. So the Dows obviously were, not obviously, but that was actually why they were built, is to drive up to tornadoes and take data in them. X-band radars, just my quick diversion here, are great. They're great on mobile radars, on trucks to be mobile. You can get very good resolution, but what happens is they attenuate. So when you're looking through these big supercells and you have a lot of hail, oftentimes you can't see the back end of the storm, or sometimes the forward part of the storm, because the signal attenuates. So once you start getting up to C and then even bigger S-band, like our 88Ds, you could start seeing much more of the storm. So having a C-band allows you to see much more of the storm, also in fine scale detail, but again, like the Dow, you can't just put it on a truck. So the idea with that, for like a Perils project, which we propose to use the C-band, is that it would be more of a, I'll say, storm scale radar. So for QLCSs, you have a pretty good idea. I mean, they impact a large area. You don't know where the tornado is going to happen for sure, but the storm itself, the QLCS. So the idea would be to put that radar sort of in the center of the QLCS, because it's not getting attenuated. You could see through the QLCS. The 2-hour setup time is no problem because the QLCS is back in Arkansas, and there's no worries there. And then you fill in with these mobile radars, which are faster. And although they can't see through the whole storm, they can see the leading edge and they can get to those positions better. So the C-band is going to be used for other stuff. Again, we do other things besides tornadoes. We do, winter weather, again, storm scale stuff. This would be fine for. So even like a project like Vortex, and I know I'm talking a lot, but even like a project like Vortex 2, if you have a good idea where your target area is going to be, you could set up the C-band. And again, it's not going to be moving, but you can get extra coverage in an area that you might not have good radar coverage in for a supercell or something like that.
Cool. Well, we're coming up on just about an hour, and I know we've monopolized your time for a while, and I appreciate this, Karen. Aubrey, you want to close us out?
Yeah, and we are so excited that for Karen to be here. Thank you so much for that great presentation. That was some fascinating information. And of course, if you want to go back and watch it again, we have the YouTube link, Mid-Atlantic Chasercon on YouTube. You can also follow us on Twitter, and you can also follow Karen on Twitter. It's at Karen_Kosiba. And then we'll go ahead and talk about our last presentation for Mid-Atlantic Chasercon. That's going to be next Saturday at 11 a.m. And we're really excited because we have 3 storm chasers that are going to be presenting about some chases. So this is going to be from Chris Jackson, Peter Forrester, and Matthew Capucci with the Capital Weather Gang. So we're really excited to have all 3. And I highly recommend following everyone on Twitter, because from Karen, from Chris, from Peter to Matthew, all fantastic information, and weather Twitter is quite fascinating. So we will see you all next week at 11 a.m. and we're really excited, and thanks for joining us.